Hello. This video is going to be using a very simple system to that shows all the work versus the MATLAB demos that use pole placement. They have functions that do everything. And what I'm going to do is go through this step by step and explain why pole placement has an advantage over the linear quadratic regulator. I'm going to show how to configure the system so it's critically damped, overdamped, and how to use inverse Laplace transforms to see the effect as zeros. We're going to talk about the use of gains. You can put them in the forward path or the feedback path. In this case, only the proportional gain would be put in the forward path or the feedback path. The integrator always has to be in the forward path. And then we're going to talk about the frequency of acceleration because I've got a motion simulation here. I'm going to talk about pole zero plots. So that's quite a bit to cover with very simple application or plant. So this is the plant. It's just got a gain and a corner frequency alpha. This is where the frequency response drops down by 3 dB, and you got um, 45-degree phase lag. And then you have this could be expressed like this as a time constant. This is our controller. It's a integrator gain. Divide by S to get the integrator. Kp is a proportional gain. Then this equation is very important. This is how you define a closed loop transfer function. And if you do the substitutions, you get this. And then if you simplify this equation, you get this equation, with this being the characteristic equation. And what we want to do now is use the characteristic equation to configure or find the symbolic formulas for both overdamped and critically damped systems. So first we're going to start with a critically damped system. And you can see that this is a second order system. And what we want to do for a critically damped system is have a system with two real poles. And you can tell this is critically damped because, well, first thing you can see the two real poles here. And the big thing to notice is that the power of S, or S to the first power, is 2 times lambda, which is 2 times the square root of the 0 power of S. Now, what we need to do is equate this to this, and the 2 times lambda to all of this. So you can see that if you make Kp big, it's going to be overdamped. If you make Kp just the right value, it will be critically damped. And if Kp is too small, such that this term is less than 2 times the square root of this term, then it will be underdamped. So let's make the substitutions. So here's where I equate the two formulas, and so I have two equations and two unknowns, although this is pretty easy to solve with by hand. So I'm solving for Ki and Kp, so I have Ki and Kp. Unfortunately, MathCAD likes to display negative signs in front of everything, but I wrote it out here. And now I've got the symbolic formulas. If I know what I want to have for a response by changing lambda, I can calculate the integrator gain and the proportional gain using these formulas. So by using the system identification, I can compute these. Sometimes you can find this out by inspection. And you can see that there's a ratio, the integrator to the proportional gain. And this is always going to be positive if lambda is greater than half of alpha, which is the corner frequency. So you can see the denominator is always the same. Sometimes in examples that you see on the internet, they'll have to add an extra scaling factor because the gain coefficients don't take into account the overall system gain. So they have to have a gain factor up in front. Well, in this case, what I'm doing is I'm showing how you calculate the Ki and the Kp, because normally on a PID or a motion controller, you don't have a special gain factor out in front. So let's continue on. Oh, one thing I want to point out is that if lambda is less than 1/2 the square root of, or less than 1/2 of alpha, you can see that this would be negative, and that could work if the proportional gain is in the feedback path only. But in this case, we're going to keep the proportional gain to be positive, because that's the way most systems are. They have the KP works on the forward path, and it's working on the error between the target and the actual, or set point and process value. But since this is a motion application, I'm going to talk about the target position velocity and the actual velocity. So this is the example for the overdamped case. Got 2 poles, and the advantage here is that I can move one of these poles to be less than the 1/2 of alpha, but I have to have the sum of these 2 poles be greater than the than alpha. So here you can see these 2 values have to be greater than alpha. If they're equal to, you end up with just an integrator term, which responds very, very slowly. So now I'm going to define a plant, so we have some numbers to work with, because we've already got the symbolics figured out. So I've got a plant where we're going to have a open loop gain of 5 millimeters per second per percent. So if I output 100%, I should be able to go 500 millimeters per second. If I output 50%, I should go about 250 millimeters per second, which will be the case in the example that I have. This is the corner frequency. It's quite low. As it turns out, it's about the same as what I have in my system that I have to test with physically at where I work. And the reason why it's so low is we have a big disc on the motor that increases the inertia, which reduces the corner frequency. Now, what I want to do is increase the frequency response so that I'm setting lambda to 2 times pi times 10, which means 10 hertz. So I'm going to have 2 poles at minus 62.83. So I'm going to have 2 poles, so it acts like a low-pass filter. And for our motion controller, what we do is we have this lambda on a slider bar, so I can just move it up and down, and these values will automatically change depending upon lambda. So now let's look at an inverse Laplace transform. And as I mentioned before, we have 2 poles, and they're at minus lambda, and we should get no overshoot, because it should act like a 2 low-pass filters. But unfortunately, we do. And what I've done is I've taken the equation from above, and I have a forcing function, which is 100. So I want to go 100 millimeters per second. And if I do the substitutions for Ki and Kp and do the inverse Laplace transforms, this is the response, where R happens to be the target velocity, and this describes the transition between 0, the starting velocity, and the R, the final velocity. Now, notice that it's dependent upon lambda, and this is something that you don't get out of a linear quadratic regulator. You choose what you think are optimal parameters or weights, and it figures out what lambda should be for you. But then you got to be fiddling around with those weights to get the desired response. And here, I can just choose lambda, and it makes it very simple. Now, linear quadratic regulators have their place, especially when you have multiple input, multiple output systems. But on most motion systems, most single input, single output systems, you only need to have a lambda that you can change. And some people call that lambda tuning. Okay, so now I've copied this equation to the velocity and the acceleration, and you can see the response. And the velocity overshoots by figuring out what the roots are. I did that here. You can see the root crosses 0. That's where, or the acceleration crosses 0. That will be the peak. And you can see that's greater than 100 millimeters per second. So what happens here is that the integrator or the proportional gain is causing the system to overshoot. And the reason why is because it adds a closed loop pole, or zero. Excuse me, I said zero. So if I remove the proportional gain on the from the forward path, which means it's only acting on the feedback, you can see that there's no Kp times S term in here like there is up above. Let's go up above. You see there's a Kp times S. That is missing here. So that means that only the Ki term is working on the error, and the in both the K or the Ki and the Kp terms are working on the error in the feedback path. But there's no proportional. Oh no, this is only working on the actual velocity. And the actual velocity, this is working on the error. So now I'm going to hand optimize this term here, and you can see that this is a much simpler system. And again, I can choose response by just changing this lambda that will determine how fast this transition occurs, and that's something you can't do with an LQR. And here's the acceleration, and you can see that by calculating out where the roots are, there is no overshoot, because what happens is that the acceleration starts out at 0, it goes up to a peak, and then it comes down. I have the scale at for the acceleration at 0 to 200 millimeters per, or 2,000 millimeters per second, which is 2 meters per second. That's about a fifth of a g. And you can see that the velocity goes right up to 100 millimeters per second without overshooting. So if you need to have a system that's never going to overshoot, make sure you don't have the proportional term, and then if you have a derivative term, working on the error. Only on the actual. So let's do a actual simulation. And what I'm going to do is I'm going to simulate moving 500 millimeters in 3 seconds. Now we're going to talk about the frequency of acceleration. The formulas here are the formulas that I use that calculate out ramp times that are 1/3 of the time ramping up, 1/3 at constant velocity, and 1/3 ramping down. And these are handy formulas to know, just like the formula for the closed loop transfer function up above. So it's taking 1 second to ramp from 0 to 250 millimeters per second. And then because it takes 1 second, that means the acceleration is only 250 millimeters per second squared. So the frequency of acceleration is the time that it takes to, or the inverse of the time that it takes to accelerate and decelerate. And if you invert that, you can find that the frequency of acceleration is about 0.5 hertz. So let's do the PI controller. And I'm simulating 1 millisecond update times. This is the alpha matrix, but right now it's just a scalar because our system's so small. This is our input coupling, but it's also a scalar because we only have one pole. We have the initial velocity, control output, and the integrator term. And then what this does is it updates the state. This is my PI controller. Updates the state. It's multiplying the proportional term times the error. R is the target velocity. X is the actual velocity. And then we also have the integrator term. This is the old integrator term, and then we're adding the new term here, which is the integrator term times time. And the reason why I include the time value in there is if I don't change the response that much if I change this value. In other words, we're not dependent upon the sampling time with this equation. Now, if we made this very coarse, then obviously the control would suffer. But this updates the integrator term by itself, but notice I have limits. Now I could just limit this to plus or minus 100%, and if I did, what would happen is that the proportional term and the integrator term could both wind up to a value of over, I'll say 200, 300, and I would have to limit it here so that I don't have an output that's greater than 100% because 100% represents whatever the limit is on your amplifiers or whatever is driving your system. Now, the trick is to subtract the proportional term from both these terms, both the plus 100 and the minus 100%. And what that does is it modifies the integrator, obviously, and it keeps it from winding up. And you'll see how that works in just a moment. So here I've made a step jump, and in theory, it should overshoot. It did with the when I did the inverse Laplace transforms, but it's not in this example. And the reason why is because we're first thing is we got a limit of plus or minus 100%, whereas in Laplace transforms, they don't take into account the control output, the effort that's required to move the system. There's no limit. So in theory, the Laplace transforms could be outputting 200 or 300%. Even if you're only moving at a small velocity. And here you can see that it's saturated, the control output, that's green, and it comes down, and then finally when we get into position it goes down to, the velocity goes down to 0, and the output goes down to 50%. And the reason why is that, remember, 500 millimeters per second at 100% and 250 millimeters per second, it will be 50%. So this is exactly right. But now look at the integrator. You can see that when the control output for the proportional term went way high, we subtract that from 100, so the integrator ends up being negative, and then it integrates itself nicely into the final value. So this is a trick that avoids integrator windup. The only problem with this is that you got to make sure that your integrator is tuned correctly, or it might take forever for the integrator to wind up to the correct value. But because we are using formulas to generate what the integrator and proportional terms are, our control is going to be very, very good. And it's not overshooting because of the output limits that we have. So let's go on down and let's see a motion simulation. So I'm using a fifth order target generator, and it's using 1 second to ramp up to the constant velocity, max velocity of 250 millimeters per second, and 1 second to ramp down. So altogether, again, it's taking 2 seconds to ramp up, so our frequency of acceleration is 1/2. Now let's take a look at what happens when we use the Iminus P control. In other words, the proportional term is only acting on changes in the actual velocity. And you can see that we're not looking at the error term here. We're just looking at the actual velocity. We're using the same trick for limiting the integrator output. And but because there's no zero, and the frequency response is less, as we showed in step response, you can see that it's not following quite right. There's a little bit of phase lag. So let's use the incremental form. This is the kind of form that you would use with a DSP, and you can see that this is tracking nicely. Again, this has got the, it's a PI controller, so the proportional term is working on the error. And what's interesting to see is that the control output, goes up a little bit to compensate for the fact that some of the energy has to go into spinning the inertia, and then we're subtracting a little bit of energy out to slow the system down, do the braking. And then you can see that the actual velocity and the target velocity are almost the same. So that just shows that our tuning parameters, our formulas, are working well. So now let's take a look at bode plots. And this closed loop transfer function comes from above. And what I'm doing, this is just math that I use to calculate what the response should be, the magnitude and phase. So let's look at the bode plot itself. And what you can see is that, um, well, the frequency of acceleration is 1/2, so we got 0.2, 0.3, 0.4, 0.5 right here. You can see that there's no drop in the gain and no phase lag at that point. And that's why it follows so nicely. Now, you can see that if we were to increase the frequency or reduce the move time in our example, what would happen is we'd get some overshoot, and this bump here, where it goes over 0, that's caused by the 0. Remember I told you there's a closed loop 0. So that's caused by the proportional term being used on the error or applied to the error and not just to the actual velocity. So let's plot the pole in 0, and I want to show you how to look at this. Let me get the poles and zeros up here. Okay, so you can see that the poles are where we want them to be. There's 2 of them. They're right here, and there's a 0 about halfway. And what you need to do is start from the origin and scan out. And you can see that if you hit a 0 first, it's going to affect the system before the poles will. So what happens is this starts adding phase lag and gain, and that's what causes that bump, for the gain and the phase lag to go high. And then what happens is finally when the frequency gets to this point here, we have 2 poles. So one pole will cancel out what this 0 is doing, and the other pole will cause 50 or the 90 degrees of phase lag. And that's basically what you see right here. It goes up, and you can see here the gain's a little bit high, and then it goes down to 90 degrees. And this is because there's only 1 0 and 2 poles. Now let's go do the Iminus P version, and this is where there's no proportional term in the forward path. And you can see that this is very simple. You can see there's no overshoot, but because there's 2 poles and no zeros, the eventual phase lag goes to 180. And you can also see that the reason why the response up above, when we were doing the simulation, why it wasn't following so well is that if we take a look, that's 0.2, 0.3, 0.4, 0.5, you can see that there's some phase lag right here. And so I can take a look at the bode plot, and I can tell what approximately how it's going to respond at each one of these frequencies. So let's go on down and plot the poles. And the poles will be the same. There just won't be a 0. So let's look at the overdamped response. And like I said earlier, lambda and mu have to be sum up to be greater than alpha. And in this example, they are. Alpha is 6.2. Now, they're quite a bit more, so the response here is going to be actually pretty good for an overdamped system. And this is the formula for Ki and Kp, but this is much less than the gains from above. And this is the same PID routine. And you can see that it does the step jump nicely, but this scale this is 6 seconds instead of 1. So it's taking a lot longer to get to the set point. And then we're going to do the same motion simulation, and you can see that it's lagging quite a bit. And we're going to see you've got both a decrease in amplitude and a decrease in phase. So that explains why the response isn't as good as it should be. And again, if I try moving that motion, making it faster, it's going to be worse yet, because we're going to be moving. We'd be looking at here, say if we had a frequency of acceleration of 2 hertz. So we're going to plot the poles and zeros, and here you can see the poles and zeros almost cancel each other out. And the reason why it responds as well as it does is these do cancel out. And basically, this is the pole that makes all the difference. But these pole and zero cause the extra, or they cause the extra phase lag and decrease in gain. So again, just want to go all the way to the top here. Hopefully this is easy enough to follow. It might take a little bit of work to convert this to this by hand. If you have a computer algebra system like MathCAD or Mathematica, maybe even MATLAB, Python, it can do this conversion for you. The big thing is that we can calculate what the response is going to be by choosing lambda. And then because we have these formulas, we can change the gains here depending upon lambda very easily. What's also interesting is that if the gain or the alpha change during operation, we can update the gains automatically. I've got a video that does that. So again, I want to emphasize that we can choose where the gains are. We have shown the difference between critically damped response and overdamped response. And normally what you want to use is critically damped response. That makes it easy to determine where the poles are. And then using inverse Laplace transforms, you can see if there's a potential for overshoot due to the zeros. And I talked about gains in the forward path versus the feedback path only. And I've shown the bode plot and how you can take the frequency of acceleration and look at the bode plot to see what your response is. And then finally, I showed where the zeros are. So that completes my video. Hope you enjoy it. Bye.